Let's go ahead and solve the system of ODEs. This is a challenging one. It's challenging because, to begin with, you're not given a single equation that has only one variable. But both of these equations involve an x1 and an x2. But what we can do is we can solve for x2. And you're going to notice that everything else on the left is in terms of x1. So then we can then go ahead and just divide this over to this side. And this is what we get. We can then take this and plug it in to the second equation. So if we do that, taking the derivative is going to yield the following. So the derivative is linear, so we can just apply the derivative twice to x1. So we're going to get x1's going to be, you're going to be taking fourth derivative, and x1 is just twice. Now we have a negative k, and we just go ahead and plug this in. So we're going to have m1 over k x1 double prime plus x1, and we're going to be subtracting x1. So then to reduce this, we have that these x1's cancel. We go ahead and multiply m2 m1 over k x to the fourth derivative x1. And then we go ahead and put here x1 double derivative. So in parentheses, we're going to have an m2 from the left. But from the right, you're going to go ahead and add m1. And this is what we get. So what did we do? We started with things, ODEs, which involved x1s and x2s, and we created a new equation. In this new ODE, we can solve. So how would we solve for this? We would use the characteristic equation. So what we have here is m2 m1 over k r to the 4 plus r squared. m2 plus m1 is equal to 0. Factor out the r squared. You're going to get m2 m1 over k r squared plus m2 plus m1 is equal to 0. So we get that r squared is 0. So 0, is a double root. And then we're also going to be getting r squared. We're going to subtract m2 plus m1, and we're going to divide by this quantity. So we're actually multiplying by the reciprocal. So we have a k at the top, and then we have an m2 times m1, so we're going to get a negative 1 over m1 plus 1 over m2 times k. So then r is going to be plus or minus I and the square root of 1 over m1 plus 1 over m2 parentheses times k. So let's, for the sake of notation, go ahead and call this alpha. So we were just solving for x1. So the general solution for x1, let's go first and take care of the double zero. So the double zero, what do we have? We have it's e to the 1, e to the 0, which is just a constant, but since it's double, we're going to have a plus bx. Now, for the imaginary part, what we're going to get is we're going to add another constant times cosine of alpha. And actually, instead of using x, it's going to get confusing. So let's go ahead and use t's. So then we have a t here, and then times sine alpha t. So this is the general solution for x1. We now want to find what x2 is. We can easily find x2 by looking up here and using this equation. We can take its double derivative and we could easily find it. But, however, it's going to be easier first if we figure out what these constants are. And what we can do is, since we just figured out what x1 is, we can use the first equation, this one here. So let me go ahead and copy that with our initial conditions and go down to the bottom where we left off and paste these here. So how is this going to help us? Well, let's go ahead and calculate the left side of this. So move this over to this side. Let's go ahead and calculate the double derivative of x1. So when we're calculating the derivative, look at the first terms, a. We know that the derivative is linear, so let's focus on that. If you take its derivative once, that becomes 0. So that's going to be gone. Now focus in on b times t. If you take the derivative of that once, you get b, but if you take it twice, it becomes 0. So the only thing that remains in reality is going to be the double derivative of that. So what we have is m1 times the double derivative of what I have underlined on the far right. So if I take the derivative of cosine and then twice, I'm going to get back with sine. However, in the meantime, while I did that, I'm also going to get a negative from the derivative of cosine. I have c, but chain rule tells me I also got to take the derivative of the inside, and I do that twice, so I have alpha squared. Now, the derivative of sine gives us cosine, and then the derivative of cosine gives us sine again. So actually I did a typo here. So actually what I want here, not sine, but is cosine. And then on the right, I'm going to get sine alpha t. I get a negative from the derivative of cosine. I still have the d, and I took the derivative twice, so chain rule tells me I need that twice. Alrighty, so then we can now go ahead and plug in our initial condition. So let's go ahead and start off with the first one. So the first one, if I plug it in, they both have the same initial condition. So I'm just going to get 0 on the left. So this is when t is equal to 0. I'm going to get the following. I get a 0 on the left. And on the right, I'm going to have my m1 times negative c alpha 2. And if I plug in 0 here, I'm going to get just 1, while on the right I get 0. So therefore, the conclusion is that c is identically 0. So then, taking our red marker, we can just scratch this off since it's 0. Okay, now we want to use the second initial condition. So then taking the derivative of this formula, well, I'm going to get k, that's a constant, x2 derivative minus x1 derivative is equal to m1 times x1 to the third derivative. So we can go ahead and take the derivative one more time, and what we're going to get is negative d alpha to the 3 cosine alpha t. So all I did is I focused my attention here. So I already knew that this was gone since c is 0. And so I had already taken the derivative twice. All I needed to do is just take it one more time from here. So I took the derivative of the sine, got cosine, I got an alpha that came out. So plugging in the initial condition on the top right, I plug in 0. Then on the far left at the bottom, I'm also going to get 0. So this is when t is equal to 0. Go ahead and plug it in. So on the far right, if I plug in 0, I'm going to get 1. So I'm going to have negative d alpha to the 3. So then therefore the conclusion is that d is also 0. So then what does this do to the original x1? Well, we already know c is 0, and now we've just concluded that d is 0. So x1 in reality is this. All right. So then now we need x2 as well. Well, using the same equation on the top right, on the top left, I mean, we can figure out what x2 is. So we know that k, x2 minus x1. So what is a x1 again? It's a plus b t, and of parentheses, is equal to m1 times the second derivative of x1. But again, if you take the derivative of a once gives you 0, and if you take the derivative of bt twice, you're going to get 0. So in reality, times 0 is equal to 0. Dividing the k over and solving for x2, you're going to get that x2 in reality is a plus bt. All right, we're almost done. Well, we can use the initial conditions to again solve for a. We were told that if you, going up a little bit, if you plug in 0, so looking here at the top right, if you plug in 0, you're going to get 0. So x1 of 0, in both cases, you're going to get a. Therefore, a is 0. You're also told if you examine the derivative and plug in 0, so the derivative is just b, you're going to get a. Therefore, b is a. So at the end of the day, we have that x1 is equal to x2, and it is equal to a times t.